Skipping ahead to section 18. Section 18 is a revisit to the ideas in sections 12 and 13. In section 12 and 13, we talked about confidence intervals and hypothesis tests for a population mean using the sample mean, but we assumed that you knew the standard deviation of the population in order to do it. This made our procedures easier, but it's also a bit unrealistic because, of course, in general, you don't know anything about populations. Populations are too much to get data from. So a more realistic situation is that you have the mean of a population. You're trying to estimate it in one sense or another with the mean from the sample, either looking for some walls for it, confidence interval, or testing a theory about it to see if it's plausible, hypothesis testing. But you don't know the standard deviation of the population. So Section 18 will revisit those ideas and see how to adapt them for the more realistic scenario. Suppose we have a population with mean mu and standard deviation sigma, but they're both unknown, which is probably the situation you find yourself in usually. We don't know the average of all the numbers in the population, nor do we know how all the numbers in the population vary. But we have taken a simple random sample of size n from that population, and we've averaged those together to get the sample mean. So how to use the sample mean x bar to estimate mu under those conditions. We know in theory that the distribution of the sample mean x bar, right there, is that it's approximately normal shaped with mean mu and standard deviation sigma over the square root of n. This is true either because what you're picking from has the normal shape or because the sample size is large. And of course, there's all kinds of reasons why we want to be using large samples now anyway. However, you want to understand what probability is. Probability is the study of uncertainty. And as always, it depends on what you know. If you know that a die is fair, then you know that there's an equal chance of all 6 numbers coming up. If you know something else about the die, then you have different probability rules. There are certain things you assume in the absence of anything else, that the die is fair, for instance. But bottom line is that probability is subjective, because of course it depends on what you know. In other words, there is no such thing as an objective probability distribution. To say that any variable has certain probability rules is to say that it has those probability rules based on what you know at the time. There is no objective sense in which a particular variable obeys certain probability rules. Probability, remember, is the study of uncertainty. It depends on what you know. So there is no objective sense in which this variable obeys these rules. It obeys these rules under certain assumptions that we normally have, but now we have to rethink them. Now, everything we do with confidence intervals and hypothesis tests is in one sense or another, in section 12 and 13, based upon this formula. Of course, we don't know mu. That's the whole point. That's all baked into this from the outset. But the ability to use those rules in sections 12 and 13 were predicated on the assumption that we know what's in the second blank. We know the standard deviation of the statistic. The bottom line is the less you know, the more you have to estimate. And the more you have to estimate, the less sure of your facts you are. And the less sure of your facts you are, the more uncertainty is in the mix. The less certain you are about everything, the more randomness is inherent in the variable. In other words, the less sure of your facts you are, the more random the thing is. So we do the obvious thing. If we don't know this creature, well, of course we know the sample size. So in particular, if we don't know this creature, sigma, then we're forced to estimate it. However, if we're forced to estimate it, we're introducing uncertainty into all this. And uncertainty increases randomness. So the bottom line is that the creature in question is more random than it would otherwise have been. In other words, the probability is more splayed out from the center than it would have been. It's less clumped up tightly around the center. You're more likely to be far away from that center. You're less likely to be close to that center. That's the logical conclusion from introducing more randomness into the mix, which in turn is the logical conclusion from estimating something about which you were previously certain. So that's basically what I'm saying in these paragraphs. There's no such thing as objective probability. Ultimately, the shape of this probability distribution comes down to what you know. Again, it's all right not to know this. That's part of the whole thing in the first place. But everything we've been assuming about using this, assume we were able to fill this blank. And if we're not, then that makes things a little bit more complicated. If you're working with less certain knowledge, then X bar's probability will be a little bit more spread out, less clumped up around its center than it would otherwise have been. You're less sure of your facts. In other words, it's going to be not quite normal shaped. I'll show you what this looks like a bit later, but instead of our typical bell shape, it's something that's almost our bell shape. It's got a little more area far away and a little less area close up. I'll show you what that means as we go on, but let's start with the basics. If we don't know sigma, then in order to even begin this process, we're forced to estimate sigma with whatever we got. Now, just as the proportion of successes in the sample, p hat, estimates the proportion of successes in the population, p, just as the average of the numbers in the population, x bar, estimates in the sample, just as the average of the numbers in the sample, x bar, estimates the average of the numbers in the population. Likewise, if you don't know how the population varies, then your estimate of that is going to be how the sample happens to vary. In other words, the standard deviation of the numbers you pick, section 2, S, data, estimates the standard deviation of the population, how the concept varies. So the bottom line is we're using S to estimate sigma. Now, if you have n numbers from the population, in this case, in 100 people's heights, or 50 people's incomes, or 17,000 rolls of a die, or whatever it is, you have so many numbers, you have n numbers. If you have those 100, 200, however many numbers, then you know what they average up to, x bar, and you know their standard deviation, S. The old section 2 data standard deviation. It may be tedious to compute, but if you have 100 numbers, you have x bar and you have S. You have their mean and their standard deviation. The only difference is now we're going to need to use S. Now, of course, S is tedious to compute at the best of times, and of course the average of 100 numbers even is tedious to compute. So we'll typically start out with x bar and S already given to us rather than all of the numbers. But in theory, if you've got n numbers, you've got their x bar, their S. They're easily computed. It may be tedious, but it's not hard. So if you're using S to estimate sigma, then you're literally introducing another dimension of randomness into the mix. You are estimating this in order to find the rules which will enable you to estimate this. So our process is going to be that much more unreliable. The more random this is, the less it's able to estimate mu. We've seen this before. What does this mean in practice? It means that confidence intervals are going to be a little wider than they would otherwise have been because there's more randomness involved. If x bar isn't as likely to be close to mu, you're less confident of the results. So compared to if you weren't estimating sigma, confidence intervals are going to be a little wider. A 95% confidence interval will be wider than before if you have to estimate sigma using S. As for hypothesis testing, let's think it through logically. H0, remember, has the benefit of the doubt up to a certain point. until things bounce too far away from other things for that theory to be plausible any longer. HA has the burden of proof. So if there's more randomness involved, then H0 will be plausible a little longer. It isn't so weird to get a sample as far away from you as it would have been. So compared to if you weren't estimating sigma, H0 will hold out a little longer. It'll be a little harder to reject. HA won't come into it quite so quickly. It'd be a little harder to find evidence of HA. Those things will take care of themselves, of course, when we go to do the numbers, but that's the logic of what we're doing. So what we have is that having to estimate sigma using S literally contorts the probability distribution of X bar so that it's no longer quite normal shaped. It's what we call a t-distribution. And first of all, you have to understand that there's more than one t-distribution, but they basically look like this. Now, in this little diagram here, the black one is the normal shape, the standard normal curve, centered at 0, standard deviation 1, RZ. There are many t-distributions. Let's focus for a moment on this first one, the yellow one. You can see how this plays out. It's got roughly the same shape as the normal distribution, but it doesn't peak quite so high, and off to the sides it's a little higher. So in other words, compared to the normal shape, the black one, you're less likely to be close to the center and you're more likely to be far away from the center. The randomness is more spread out away from the center. Things are more random than they were. So that's the logic of the t-distribution. Now, as to there being more than one of them, in fact, there's an infinite number of t-distributions. What we talk about is the t-distribution with 1 degree of freedom, the t-distribution with 2 degrees of freedom, 3, 4, 5, forever and ever. There's an infinite number of t-distributions. Now, I want to be understood properly on this. Back in section 3, we said there was an infinite number of normal distributions, but there's only one standard normal distribution, the normal distribution with mean 0 and standard deviation 1. So this is not like what we were seeing before. These are not different examples of a normal shaped curve. These are things that are not quite normal to varying degrees. The yellow one, of course, is least like the normal curve, and the blue one is a little bit more like the normal curve, but it's still not perfect. So, in the sense that there is only one normal distribution, the standard normal N01 normal distribution, the one on our charts. In that sense, in the sense that there is only one normal distribution, there's an infinite number of t-distributions. In other words, when we get to that point where we've standardized things, subtract the mean, divide by the standard deviation, there's an infinite number of these t-distributions to cope with. This is not as complicated as it sounds. The t-distribution has one less degree of freedom than the sample size. So, for instance, if your sample is size 100, you're using the t-distribution with 99 degrees of freedom. If your sample size is 6, then you're using this blue one, the t-distribution with 6 minus 1, 5 degrees of freedom. We'll summarize all this in a moment. Now, if you look at the t-distribution with 1,000 degrees of freedom or 1,000,000 degrees of freedom, note the trend here. 1, 2, 5. The bigger the degrees of freedom, the more tightly it's going to hug this normal curve. So the t-distribution would say 100 degrees of freedom is going to hug the black one pretty closely from above here, pretty closely from below here, and pretty closely from above over here. In other words, for the yellow, for the blue, for the purple, even for the blue, you can sort of see the difference. But by the time you get to the t-distribution with 100 degrees of freedom or 1,000 degrees of freedom, it's going to be virtually the same shape. It's going to be hugging it tightly on the inside here, hugging it tightly on the outside over here, but you're not going to see the difference with the naked eye. That's why we refer to the normal distribution as the t-distribution with infinity degrees of freedom. For instance, if you talk about the t-distribution with 1,000,000 degrees of freedom, then for all practical intents and purposes, it's the same shape as the normal distribution. It's just the tiniest bit different. So for very large samples, we'll say 1,000, you're not really going to see the difference between the t and the z. What we're talking about is for small samples. We talked about this back in section 12 and 13 briefly. For very large samples, whether you talk about t or z is not really going to make a major difference. Say 1,000. But for smaller samples, it can make a major difference. If you're looking at the purple one instead of the black one, or even the blue one instead of the black one, it can make a bit of a difference. So we are talking about something that is useful for smaller samples. Now, in theory, this plays out pretty much exactly the same as it did before. If you want to standardize, if you want to go to the t distribution, then we do exactly what we did before. You take the sample mean, subtract what you're assuming to be mu, and divide by, well, if you're turning it into z, it's sigma over the square root of n. But since we're forced to approximate it, it becomes a t. The fact that this is s instead of sigma, the fact that it's the sample standard deviation rather than the population standard deviation, the fact that it's how the sample happens to vary rather than how the population really does vary, the fact that we're using s instead of sigma means that you have to make this t instead of z. It is the substitution of s for sigma. It is that estimating which turns it from a t distribution, turns it from a z distribution into a t distribution. We talked about this idea before. If you're forced to estimate the standard deviation of a statistic using sample information instead of population information, then it's called the standard error of the statistic. The standard error is our estimate of the standard deviation of a statistic. The standard deviation of x bar is sigma over the square root of n. The standard error, our estimate of that, is s over the square root of n. We've seen this before. It came into it briefly in section 10. It came into it a lot in section 14 when we talked about the pooled standard error, our best way of estimating that thing we didn't know. So in the sigma unknown version of our procedures, this becomes important. But the bottom line is using s instead of sigma makes it a t distribution. In theory, this is no big deal. In practice, it becomes a little tedious. For confidence intervals, this plays out pretty much exactly the way it did before. You're just using a t-chart instead of a z-chart. For hypothesis tests, if we're using charts, and of course we are, then it becomes a little bit more complicated, and I'll show you how that works. But it's not a complication in the theory. It's a complication in our resources at hand. So that's basically the theory of what we're talking about here. Also, a few words on the t-distributions here. The t-distributions work more or less like the z-distribution did. The total area is under it is 1, of course, because it's a density curve. It is symmetric about 0, and it extends infinitely, just like the normal one did. If the degrees of freedom is very large, then it is approximately the standard normal curve, the one in our z-charts. But for smaller sample sizes, you can see the difference. I would say that it's almost normal, to coin it a phrase. Notice the way these look. Now they're overlaid, so you can't really get a good look at them, but we're not talking about thinner bells like we were in section 3. We're talking about things that are not quite bell-shaped. If you look at the yellow or the purple or even the blue, you'll see that there's something a little funky about them. They don't look quite bell-shaped. Overlaying them, you don't see it quite so much. But the black one, the normal one, has the perfect bell shape. The others are not quite bell-shaped. Notice, by the way, that when we were talking about thinner normal curves, this inflection point, this place where the steering changed, was a smaller distance. Here it's not. Here it's still that same distance. But you can see how this plays out. When we pass from the shorter ones to the taller ones, it doesn't change that distance. It just changes how you pass through it, but it's exactly the same distance as it always was. So in order to do these problems, we need a t-chart. There's a t-chart available on my website. You just go scrolling down to t-distribution, and then it pops up. Let's make it a little bigger. A lot bigger. So these are the way the t-charts work. Now what you want to understand is that we have information for the t-distribution with 1 degree of freedom. We have information for the t-distribution with 2 degrees of freedom. We have information for the t-distribution with 30 degrees of freedom, and so on and so on. And like I said, the infinity one is basically the normal chart. So we have information for the infinity degrees of freedom, the normal distribution. And these numbers should look a little familiar. For instance, the 95% corresponds to our old friend, the 1960. And if you're talking about the t-distribution with 5,000 degrees of freedom, you're not seeing a lot of difference. Point is, every one of these rows corresponds to a complete chart, like the z-chart, which we do not have. So for confidence intervals, this is no big deal. You just look the number up exactly as you did before. 95 column, pick the entry. For hypothesis tests, we're going to have to be a little bit more clever. The analogous thing here is that it's like trying to do the previous hypothesis tests simply using that confidence row rather than the full chart. So we have a bit of a limitation on our resources at hand. Again, every one of these rows is the corresponding thing to one of our z-charts. There's an infinite number of t-distributions, but we can't have an infinite number of t-charts. So we're forced to make do. We have this going for us for hypothesis testing. We don't really care what the p-value is. The only reason we ever compute the p-value is to decide whether it's literally unacceptably small. Is it less than 5%? In other words, as I've said before, hypothesis testing is the one time that close enough is good enough. We don't really care what the p-value is. We only care about the answer to the question, is it suspiciously small? So we don't actually need to compute the p-value. It's enough to ballpark it. I'll show you how that works when we do some practical problems. But it does mean that confidence intervals are going to be pretty much exactly they were before, just using a different row here. Hypothesis tests, in order for us to do them, we're not going to be able to compute the p-values now, but we can still ballpark them, and that's enough. And that's what I'm saying here, basically. Confidence intervals work almost exactly as before. We're simply using a different row for the reference. However, we cannot compute the p-values for the hypothesis tests. We don't need the p-values. All we need is a rough idea of whether it's suspiciously small, and that we can pull off. I'll show you how we do that. So the bottom line is that everything that was previously a z is now a t if you're using s instead of sigma. If you are forced to use s instead of sigma, if you use how the sample varies rather than how the population varies, then t is the price you pay for that additional uncertainty that you're introducing, the additional randomness. So it's the exact same confidence interval formula as before, but the fact that this is an S makes this a T. And again, the degrees of freedom, the T distribution that you use, is 1 less than the sample size. For hypothesis tests, it in theory plays out pretty much exactly as before. It's supposed to be x bar minus mu divided by sigma over the square root of n gives us our z. But again, because we're using s to estimate sigma, the t instead of z is the price we pay for that additional randomness. Here we have some technical conditions for when this is considered good. We don't really have to go into it. The bottom line is that the problems I give you will be doable. So that's the theory of how the t-distributions work. I'll tackle the actual practice of them in the second part of this video as we go through the examples.